Recording. I'll start the video. Please let me know if you can hear it.
So I want to do a brief introduction. Jim Hines and I have been very good friends for a very long time. And so I thought it appropriate for me to give you a little background on where the molecules come from. So fundamentally, some people are much better at building models than other people. And Jim asked himself this question, why is that? Is it aptitude? Is it experience? Or is there something else that's going on? And Jim said, well, it's a little bit of aptitude, a little bit of experience. And of course, he was rather vain, so he thought it's good looks as well. But it turns out that there's something else that is going on. Its molecules are a way of instantiating some of the basic building blocks that people have in their brains who are good at modeling. So they're small pieces of structure. They encapsulate expert knowledge. And they bring to a model more than just stocks and flows, which are the basic building blocks from which we can create all of our models. Molecules are also neat because they have interesting properties in their own right. And combined together, they form complete models. And Jim will be giving you an example of how that can be done to form a complete model. They create a shorthand for getting to simulating models, and they provide a lot of cognitive support in the modeling process, so you can better understand both where your model is coming from.
Oh, sorry, I forgot that I put this on 1.25 speed. Is it too fast?
Sounds okay.
Sounds okay. Okay, I apologize because I usually watch things on 1.25 or higher.
From and what the components of it are. So molecules have a long history. Actually, as a PhD student, Jim started arguing about common structures. And you'll see in the molecules something called the Hines coflow, because Jim said this is a different way of presenting something that's commonly used that will be much more informative to people. And he took that interest in pieces of structure to sort of the next step and said, maybe I can collect small structures that are used again and again by different people in publishing, in sort of building models, and make use of those, make them available to others. So the sources of those small structures include published models, teaching material, and project work that's been done by Jim, his colleagues over the years. The raw molecules or building blocks are then organized into a set of relationships. And this relationship set is one of the foundations, it was one of the things Jim was talking about a lot today. But it's a conceptual frame using inheritance that allows you to figure out where the different molecules fit into things. And it's an attempt to mimic the association that experienced modelers make. So that using the molecules allows you to have more of the insights into how models can be structured that the very experienced modelers have. So the current version of the molecules is really, really cool. What Jim has done is taken documentation, which used to be just a Word file, and put it together in a form that parallels the structure and navigation of the molecules that can be used in software. And of course, the software implementation, which is now Stella, is also really, really cool. And you will find that moving back and forth between these two can be a little bit confusing because they look so similar at times. But between the two of them, you can both gain the knowledge that's there and have the working pieces to look at, play with, and paste, as we'll see, into a model that you're trying to create. So the current set of molecules are a little bit more articulation, especially related to financial modeling. And they allow you to go through and build models. What Jim is going to do today is kind of present some of the different molecules, the hierarchy that he uses to show how they relate to one another, and give you a demonstration of building a model using the molecules. Not only building a model, but conceptualizing the model. So starting from a causal loop diagram, figuring out, well, what molecules are involved in this and how do they relate to one another, and then showing you the process by which you can integrate those molecules into a working simulation model. So without further ado, I'm going to turn it over to Jim and let him continue with the presentation.
Thank you, Bob, for that nice introduction. Imagine that you want to build a model, and you open up Stella and you see what you're seeing now on the screen. A blank canvas and some very tiny objects, a stock, a flow, a converter, and a connector. Somehow you have to, from those four elements, you need to construct your entire beautiful model. If you're feeling a little nervous or a little overwhelmed, it's not surprising. You're in the position of a carpenter who wants to build a house and has on hand a huge pile of 2x4s and a big old bucket of nails. If he wants to build a house out of those two elements, it's no wonder he's feeling a little nervous. Fortunately, in this modern world, the carpenter can use prefabricated components. He can buy a door that's expertly manufactured, much better than he could do it on his own. He can buy a window expertly manufactured, better than he could do on his own. And in that way, he can get his house built faster and at higher quality than he could just using the 2x4s and the nails. Well, you and I are in the same position with respect to these small components as the carpenter. And just like the carpenter, fortunately, there are prefabricated components. And those prefabricated components are the molecules. So let's take a look at one of the molecules. This is a molecule. It's a bathtub. You're probably all familiar with this sort of structure already. You already have this molecule in your head, in your mental warehouse, where all molecules eventually should reside. A bathtub is simply a level with an inflow and an outflow. And the documentation explains that although only two flows are shown here, this molecule can have any number of inflows and any number of outflows. Just a word that just a note that you'll see in all of the molecules reflect my bias of always using biflows for stocks, biflows for flows and stocks that can go negative. The reason for that is that I believe in knowing what the structure is I'm using, and also there are some molecules that can accomplish the same thing as a uniflow or a level that doesn't go negative, but can do so much more elegantly than the built-in options in Stella. So let me go over this a little bit because the same sections in this molecule hold for all molecules. First of all, you'll see a title and then a diagram. You'll see appearance and something called ultimate appearance. The bathtub doesn't have those. We'll talk more about that in a moment. Then you'll see the children molecules, and we'll talk more about that in a moment. And then you'll see a section on the problems that the molecule solves. So all molecules solve one or more problems. In this case, this molecule solves the problem of how to accumulate an inflow and deaccumulate an outflow, or how to increase and decrease something incrementally. The equations come next, and you'll see that here the inflow and the outflow are blank, and that's because the molecule does not specify the inflow or the outflow. And similarly, in other molecules, you'll see other variables with a blank. That's because the molecule itself does not specify those variables. The next item is a description, and this just tells you. It just describes the molecule a little better. This one starts out, a bathtub accumulates the difference between its inflows and its outflows, and it goes on from there. The next section will show behavior. In this case, it shows the behavior of a level rising linearly in the situation that the inflow is greater than the outflow. Next up are classic examples. This one starts out suggesting that a workforce might be represented as a bathtub. The next section is caveats. This one mentions the possibility of bathtubs going negative with this molecule and warns you about it. And then in the technical notes, which I always find very interesting myself. Well, I find them interesting. These technical notes explain the simplest ways that the simplest molecules available to keep a flow from going negative and from keeping a stock from going negative. There are, let me tell you again, stress again, that there are other molecules that are much more elegant than these for accomplishing the task, that may be more realistic and give you better dynamics. Okay, now looking at this molecule here, you might say to yourself, "Oh, that's so sad. He's lonely, all by himself." But in fact, he's not lonely. Here is a hierarchy of the molecules, and here is the bathtub in that hierarchy. Now, this hierarchy is a hierarchy that shows it might be called a derivation hierarchy, and there are other kinds, but this is the kind that I think is best for learning the molecules. For example, if you look at the bathtub, which we just saw, has a child, which is a first order smooth. It adds to the idea of a stock and a flow the idea of a very specific way of formulating that flow. And if we come back here, the way of formulating that flow is another ultimate molecule that is called the goal gap. And in the goal gap, there's a goal, there's a variable. In the case of a smooth, this variable is the stock. There's a gap between them, and then that gap is converted into an action or a flow by dividing the gap by time constant. In the smooth, this action or flow accumulates into a stock. So what can you conclude from that very quick description of this hierarchy? One thing you can conclude is the children tend to be more complicated than their parents. And so if you want to learn the molecules and you find a molecule that is a little confusing to you, the way to understand it is to back up and look at its parents. And in the case of some molecules, you can back up more than one level. So here, if you don't understand the C anchor and adjustment, you can take a look at the first order smooth. And if that is hard for you to understand, you can look at the closed gap, and you can look at the bathtub. Those are simpler molecules. The other difference that can occur between parents and children is that parents children can be more specific than parents. So for example, we just looked at the first order smooth. If we look at the workforce molecule, well, the workforce is really just a more specific form of the smooth. It actually names what the level is, it names what the gap is, it names what the goal is, what the flow is, and it gives a name for the time constant. Whoops, that's a little too small. Okay, let's see. If you haven't gathered yet, the molecules that are in the yellow boxes are ultimate parents. They're the molecules that have no parents. It might look like this has loops in it. It does not. Everything traces back to one of these ultimate parents that have no parents. So there are no loops here. Okay, let's take an example. Let's say that you have a client, and this client manufactures cowboy boots, but not just any boots, very fancy, very expensive, very high-end cowboy boots like these pictured here, which have full quill ostrich skin on the lower areas here, which is called the vamp, finest cow skin on what's called the shaft, with hand-stitched embroidery, and inside there is it's lined with pig skin, so it's as comfortable on the inside as it is beautiful on the outside. So this is it's a wonderful client. They do great work, but of course they have a problem, or you wouldn't be working with them. The problem is if they have oscillations. Inventory goes up and down, and so do workers go up and down. These oscillations are very hard on managers. Both oscillations are very hard on managers. The oscillation of workers is also very hard on the workers, obviously. So with that, explanation of the problem, let's think about the process that you use just before you get to the actual modeling stage, the simulation modeling stage. Well, the first thing you do is you come up with some hypothesis for the behavior that we just saw, that oscillating behavior, a dynamic hypothesis, or many dynamic hypotheses. And let me show you the dynamic hypothesis that you have already come up with. So let me just do that. So here is your dynamic hypothesis. Those of you with a keen eye will immediately recognize this as the workforce inventory oscillator, but pretend that you don't know that. And if you don't know that, if you really don't know that, well, you're in great shape here. So let me build up this this causal loop diagram from piece by piece. So the first part of it, we might say, is there's an inventory, and there's producing that increases the inventory, and there's sales that decrease the inventory. Simple enough. Where does producing come from? Well, more workforce will increase our producing. Where does the workforce come from? Well, it takes time to hire and fire people, and so the workforce comes from the desired workforce. And the more desired workforce, the more workforce. And where does the desired workforce come from? Well, it comes from sales, because if we have the desired workforce and the workforce, just the right workforce, to produce at the level of sales, then the increase in inventory caused by producing will exactly match the decrease in inventory caused by sales, and inventory will be unchanging. Now, it could be that you want to change the inventory because that constant level of inventory is not where you want it. And so there can be an inventory correction. and so the workforce, desired workforce, has two influences. One is sales and one is inventory correction. The greater either one of those, the greater our desired workforce will need to do some producing. And the inventory correction comes from an inventory compared to desired inventory, and that somehow produces the inventory correction. Okay, I hope that's clear for you. Now we want to convert that into a simulation model. Oops. Into a simulation model. Oh. And so we have here a sort of a bit of a prefabrication here. We have the our causal loop diagram, and then here we have steps. Our first step has already been taken. That's the causal loop diagram. Our second step is what we want to do is we want to look at this causal loop diagram and actually figure out where the in order to represent something like the workforce, what molecule can help us there. Ideally, we want to do that before we start modeling, particularly on a causal loop this simple. Here, though, what we'll do is we'll do it step by step. So the first step shows our causal loop diagram here, and it says that we figured out that we can use our old friend the bathtub to represent producing, inventory, and sales. Well, where do we get that bathtub? Well, if we come back to the hierarchy and the documentation, you'll see a little item here that says Stella models of molecules. Let's do that now. So I just clicked on the button, and now Stella Online, the reader, is coming up, and here we have the same. We have the molecules, and one thing you'll notice, and this will come again and again, is that this picture looks exactly like this picture, except that this picture, the model documentation, has a sandy colored background, whereas waiting for it. Whereas this this background, which has the models of molecules, has a white background. This is in Stella Online Reader, which means that you can double-click things, and you can play with the molecules if you want. You can you can play with them, and you can see the equations, etc. But you cannot change the equations, and you cannot copy and paste. And for that reason, I would suggest you either download the model to your own copy of Stella Professional or Stella Architect, or you transfer this Stella Online model to your own online account, your own online professional account, which will allow you to cut and paste, change equations to your heart's content. Let me show you so I have done that, and so here is the molecules, and now if I click on bathtub, we can see a model of the bathtub. And a nice thing that we can do now is that we can copy and paste it. And we will do that right here. So we just plop down that molecule here. Now our work is far from done. We need to rename these. We need to put in the right units, and we need to put in any equations that we need. So first of all, the level. I sometimes have trouble with this, as you can see. There we go. Instead of level, we've got, we call this just the stock of our boots. Okay. The inflow, here we go again. The inflow we'll call producing, and the outflow is selling. I like to use the present progressive tense of flow for flows, of verbs for flows, to get across the idea that it's something happening now, happening currently. Okay, And now we need to change the units. This has the original molecule had units of widgets, but we want units of, well, we could call it boots, but I prefer to have units different than variable name. So we'll call this pairs, as in pairs of boots. Okay, and that will set up the right units for producing and selling because of how wonderful Stella is. But we still may want to change the equation. In this case, it's just a comment, just a constant. Well, we'll put in 100 there for what selling is 100 pairs per week. Oh, yes, we also want to make sure that this is per week, which it is. And producing, we'll put in at 110. And obviously, we can, it's always good to simulate your model along the way. And if you do that, you can just check that it's that you understand it. The model will never be easier to understand than as you're building it, when it's simpler. When it's the simplest, it will be from now on. Okay, that's step 2. Okay, step 3 adds to, so we have our bathtub with the causal loop, and now we've got building a molecule called building inventory by doing work. And that is a molecule that is right here. That's the molecule. And of course, I could transfer all that to here the way we did last time. But just to save time, following my dear friend Julia Child, I have one in the oven. That's my best imitation of her. So we'll just see what's inside the oven. If I can. Get rid of the oven, and there we have one in the oven. This is the building inventory by doing work molecule, except I've already changed the names and I've already put in the equation. So in this case, productivity, for example, I've changed the molecule so that it's 20 pairs of boots per person per week. Okay, so let's do this. Let's see. We want to basically disconnect this. And we want to add this piece, which, if you were paying attention before, this is actually just the producing model, which is part of the building inventory by doing work. So we could have done this just with the producing piece of that molecule. But we will come up here and pull this in, and then we do need to rename this to not. Stella was trying to prevent having two variables named the same. So I added the one there, but we don't need that. And there we have it, and we can get rid of this guy. And now if we run the model, as we should often, whoops. I see. It's in equilibrium. So 5 times 20 is 100, and selling is 100. So that does make sense. If we want to see something a little more satisfying, whoops. We can change this to 6 people, and now we'll actually be able to see some behavior. There you have it. Okay, so that's step 3. Step 4, we will add to our 2 previous molecules. We'll add we'll add the molecule that combines inventory and desired inventory and gets us an inventory correction. Okay, and the molecule we want is a closed gap, which you'll remember. Is over here, right there. And but as usual, from now on, I have one in the oven, which we can take it out of the oven. And here this one, unlike the actual molecule, again, has everything renamed nicely, and the units are already taken care of. Now, to hook this up, so this says that the inventory deficit is the gap between desired inventory and the variable. Obviously, now the variable is boots. So we can just hook that right up there. Okay, and then we'll have to change this name from variable to boots. And there you have it. Okay, now moving from step 4 to step 5. We're almost there. Now this adds the workforce molecule to get at the relationship between desired workforce and workforce. And we've already seen the workforce molecule, so I'm not going to go over it again. But here we have it already set up with the right names and units for our model. So the desired workforce. Oops, why don't we put it over here? The desired workforce is, as you can see, the desired workforce is set at, right now it's set at 100 people. We'll fix that. Worker shortage is as it should be. The time to hire and fire is 12 weeks. Oh, we can take a look at this too. The time to correct inventory is 4 weeks. And desired inventory, again, is 1,000. Okay, so that's step 5. And now our final step. Oh, wait a minute. One more thing. This workforce is the same as that workforce. So we can get rid of this, make the connection, and then we just have to change the name from workers to workforce. And there you go. Okay. Now, we can move this up a bit. Okay. So now to step 6. Okay. The next molecule is where do we get this desired workforce from? And we realize that we can use a workforce from workflow. Okay, that's because what we have here is we have 2 flows, selling and an inventory correction, and what we want to get is the workforce from that workflow. We take it out of the oven, and whoops. Well, actually, we don't need that productivity because we'll use this one. But let me move this up a bit. Move this up a little bit. Move this down a little bit. So we're going to attach this productivity to the desired workforce, like that. And we need to change the name to productivity, and now we have a desired workforce, which is actually this the same as this. So we can now get rid of this. We can actually rename this before we move it, if I'm capable of that. And then we can connect this up. Okay, now the desired workforce, as we just said, comes from, well, sales, as we explained before, and from the inventory correction. And here we do have to put in the equation because this was previously a constant. And so this is just selling plus inventory correction. Okay, there you have it. And the only thing left to do is to play a little bit with our model. And we can, to help our client, to get a better enriched understanding. So we already thought that this could oscillate. Let's see if this can. And, oops. And it can, just as we thought. So at this point, we haven't learned anything. But now let's enrich our understanding. Okay. So a question is, what happens if we were to tell our client that he should go faster, that this time to correct inventory is up to him, and we will probably think, as does he, that the shorter the better. Well, let's test that out. Well, in fact, that's not true. With a shorter time to correct inventory, whoops, we have actually even more oscillations, faster oscillations. So, so let's try to do it the other way. Let's make this, surprisingly, with this working the other way, what does that do? Well, if we lengthen this, it actually makes it less oscillatory. Well, that's surprising. Why is that? Well, the reason for that is, on the one hand, if this is like pressing down on the accelerator, and so when we make this very short, we really speed up this time to correct inventory because this inventory correction, because the time to correct inventory is on the denominator, and so that actually strengthens this loop, which is obviously now we can see it's the oscillatory loop, and since strengthening it creates more oscillations, weakening it, weakening the loop makes less oscillations. Okay, so we can tell them that you've gone to all this trouble to make it really fast to correct inventory. Relax, don't do that as much, and you'll be better off. Okay, so let's look at this other constant here. And it's the time to hire or fire. Right now it's at 12 weeks or 3 months. Yeah, 3 months. And we could try again, just as we thought before, except let's get rid of all of these runs. We'll just get our base run back. Okay, and now we can see whether, well, as we saw before, the time to correct inventory got faster. So if we strengthen this, as this got shorter, the oscillations got worse. Let's try it here. We'll make this a lot faster. And unlike this time constant, playing with this one, the oscillations get much better. In fact, they go away. So we can tell our client, we need to understand this, but we can tell our client that if you want to put in your effort on reducing the time to hire or fire. For example, keep a list of your prior employees and all people in the area that have the correct skills, and then you can hire them very quickly, something like that. But there's another, but we need to understand this. Why did this occur differently from that one? Well, the reason is that this constant only affects this constant here only affects this negative loop that has 2 stocks in it. This constant affects 2 loops. Yes, it affects this oscillatory loop and it makes it stronger, but there's also a loop that has just 1 stock in it, and it also makes that stronger. And so and apparently making this one stronger is stabilizing. So this is our stabilizing loop, and we've changed a parameter that affects both loops. And which one dominates? It's the one that has the smaller number of stocks in it. And a third order loop would, if you changed a parameter that affected both a first order loop, one stock, or a second order loop, 2, if you had a third order loop, the parameter would affect that third order loop even less than the other 2. Okay, so that's pretty much what we wanted to cover here, and I just want to wrap up a bit. Let's see, where is that? Here we go. So first of all, what are molecules? What have we just seen? Well, first of all, molecules are small generic structures arranged in a hierarchy, as you've seen. The hierarchy is very good to help you learn the molecules. Start with if you don't understand a molecule, back up to its parents. If that's still not getting through to you, back up to the grandparents, etc. Molecules are also a warehouse for building models. What kind of a warehouse? A mental warehouse. The time that you want when you want to be learning the molecules is not in the midst of modeling. You want to learn it when you're not modeling. Stopping and looking through 80 molecules while you're modeling will just delay you. It will not help you. So a mental warehouse for building models. And finally, molecules are the common heritage of all SDers. They come from models built at the very beginning of the field, all the way through it, and as such, they are are yours for the taking. There were two kinds of people who contributed to this common heritage. One, and sometimes they were the same people. One is the group of people who actually created the models in which the molecules first appeared, and the second are the people who gathered them together. I'll just mention one of those, Barry Richmond, who was the founder of IC Systems, was one such person who gathered them together. He died too young, and people in the field who knew him and those who have only heard of him or read his papers, they miss him. We all miss him. If you want more on these two sets of people who delivered this common heritage to you, take a look at the acknowledgments in the documentation. And finally, where are the molecules? Well, the models of molecules are on the IC Systems Exchange server. This is the URL, and also you can get to them from the documentation, as we saw. The documentation, of course, itself is at the URL sdmolecules.org. Well, that's it. Thank you very much for taking the time to listen to me talk about molecules, my favorite topic. And now it's time for some questions.
There are questions related to the molecules and their use in constructing models.
Jim, while we're here and we're waiting for some questions, could you just give us a little history about how you came to call them molecules?
Yes. Actually, the first person to give a presentation on this sort of thing, or the first person that I heard, was Barry Richmond in the, I guess in the 80s. And anyway, he called them atoms of structure instead of molecules of the structure. And then when I decided to expand the collection and put it into a hierarchy, I misremembered what Barry had said. And so I called them molecules of system dynamic structure. And I think that was a happy mistake because, as you may know, molecules are, you can take one molecule, add another molecule, and you get yet another molecule. Unlike atoms in general, you can't build a new atom from other atoms, but molecules you can. And so I think that molecules is actually a better name for them, with full due respect and gratefulness to Barry. Barry died tragically, terrible loss to the field. He didn't die tragically. It was tragic that he died.
The next question is, will the library of molecules continue to be added
to? Maybe. It's getting to the point where I think there are almost too many molecules. If you get a huge number, well, getting them into your head is very difficult. I mean, it gets harder. I think we're probably at a good number, but nonetheless, if there are molecules that really are extremely helpful that I don't have at the moment, that may be just being invented by somebody on the call, yes, we would add those.
Related to that, someone is wondering if there's documentation on, quote, more advanced molecules, for example, ones that use arrays.
No, none of the molecules use arrays. None of the molecules I've collected use arrays.
Great, thank you. Someone asked, why are molecules called children of other molecules? Is a child a more specific version of a parent, or a more complicated, or something else?
Yes to both. A child is it's often more specific. So sometimes you get a child who is, and let me illustrate this. Sometimes you'll get a child. So for example, here is a flow from resource, which is just some resource like people or machines that work at some productivity. And then the producing molecule is exactly that same structure, except renamed. So sometimes it's just more specific. And then sometimes it's more complicated. So for example, we just saw the producing molecule, and the building inventory by doing work, which we just used, adds on the idea of that the producing is a flow that goes into a stock. So both of those. And the terms child and parent, I think are obvious from people who worked with hierarchies, but it's used in object-oriented programming. So you may have run into it there as well.
Thank you, Jim. Someone else is asking, what is the relationship between these molecules and the system archetypes?
Thanks. That's a question that comes up a lot. The system archetypes are first of all, you'll see that they're causal loop diagrams, whereas the molecules are stock and flow diagrams. More prosaically, the archetypes are the little bits of modeling of system dynamics wisdom that has come to us through the over the years in system dynamics. So they are really wisdom about the world. The molecules are for building models. So they don't have much wisdom in them except the wisdom of how to build models. So you can't look at will not get world or life lessons from looking at the molecules, whereas you will from archetypes. Archetypes are for building models that will give you insight into the world, simulation models.
Thank you, Jim. I have two questions. I'm going to ask you together, maybe. What is the difference between molecules and generic structures is the first one, and the other one is what is the difference between the molecules in Stella and those in Vensim?
Okay. So the molecules are generic structures, but the term generic structure is used loosely in the field to mean any kind of tried and true or famous model or parts of models. In fact, so for example, some people would call the entire workforce inventory model, the model that we just built, a generic structure. It's a little too complicated to qualify for what I would think of as a molecule. Other generic structures would be Jay Forrester's market growth model and perhaps the predator-prey model, et cetera. So generic structures is a very general term for well-known structures in system dynamics that you can use for your own modeling.
And then the second part was how do these differ
right.
in Stella from those that are in Vensim?
Got it. The ones in Vensim are close to this. So they're older. They were done in the 90s. This is really a major update. The ones that at least I did for Vensim, I haven't looked at them recently. It's possible that the Vensim folks have added to them. I don't know. You should take a look. But the ones in Vensim, there are fewer molecules, which actually is an advantage. Some of the names have changed here to be more descriptive. And then this area down here is new, and as are some of the other, there are some new molecules here.
Great, thank you, Jim. Another question is, this is phrased a different way, but the idea of redesigning these to serve specific fields. So for example, biomedical modeling.
Mm-hmm. Oh, is the question, can you use them?
Is that easy to do?
Yeah, so system dynamics is a viewpoint on the world and some tools. And so you can use the exact same structure that you would use for inventory, perhaps for a piece of the blood sugar regulatory system, perhaps, which also can oscillate. I'm not sure that that's a fair way to do it. But the more abstract models, the closed gap, the third order smooth, the first order smooth, the Hines coflow, the traditional coflow, protected C anchor and adjustment, all of those are applicable to any field that has dynamics in it.
Thank you, Jim. Is it possible to download the documentation of the molecules?
No, I don't think so. But you know what? You can't do it right now. But I will. Let me look into that. I'm not sure whether you can do it right now, and if you can't, I will make that possible. That's a great suggestion.
Thank you, Jim. In closing, there is a comment of gratitude to you for creating this. The concept of molecules and the documentation you've created over the years has been incredibly useful for increasing the speed that I've been able to build models and allowed me to allocate my cognitive capacity to the 10% of structures that are specific to the problem. Thank you for your work.
You're very welcome.
And thank you all for attending. Really appreciate the attention you paid. Jim, really appreciate the time you put into creating both this webinar and the molecules. And these resources, if you want to find out more about them, please let us know. We will be sending out a follow-up email with a little bit more information just to make sure that you can follow the links if you want to. Thank you.
Thank you.
Okay. So, Rafat, would you like to ask your question to the audience?
It's something that's struck. First of all, thank you for showing this presentation, Christine. I watched it, I guess, a year ago, but I still learned a lot today. And something that struck me is the process of integrating those pieces of molecules into a model. Now there is jumping between the that file and the model file, and I am wondering how would this be integrated easier into this modeling software so one can select those molecules. It's just a thought and a question that came to my mind.
Well, that's a great question, because you wouldn't know this, but we actually implemented that for version 9 a long time ago. And we had a way for you to automatically integrate any of the molecules directly into any model you're using by right-clicking and picking which one you wanted, and it would just drop it right in place. And it would also connect flows and whatever else needed to be connected, and that all worked. And then we ripped it out because the more people contributed, the thing got huge and unwieldy, and the user interface got complicated. And we decided we'd take it out and then try to revisit it some other day. But we've never gone back to that. It's a little like Loops That Matter in that way. We started that in '96, and now it's finally out.
Wow. Sometimes the ideas are too early for for the time that it became more useful. Yeah.
Well, it's not that. In '96 and '97, when Mohammed was working on adding his pathway participation metrics to Stella, he had to go home to Iran because his mother was sick and they wouldn't let him come back. And so that kind of stalled things for a while. And then when he came back, and that would have been around 2005 when we were talking with him again to try to finish it, we didn't have the time to devote to, it's a resource question. We didn't have the time to devote then to work with him to get it to work. We had other things going on. And the same thing is true for this library thing that would pull molecules in for you automatically. While we had something that worked, they didn't want to release it by the time, it was designed, the interface was, I came up with the original design, which was very simple. And then it went through several committees. And by the time, it was just this big bloated thing by the time it was done. And it all got implemented, but people couldn't figure out how to use it at that point. It was so complicated. And we just haven't had the resources to go back and do it again. We already did it once. We could do it again, but I don't know when. We talk about it every once in a while. We should do that.
Yeah.
So right now, the easiest way to do it is to just copy and paste from the structure that, I mean, that's in a model, and each thing's in a module, and you can just copy it and paste it.
Tasso, you're muted, by the way.
Yeah, thank you. Sorry, I forgot to unmute. How about, and maybe this is more for Karim, who has more experience on this, I suppose. How about a level above? We have parents and children. How about grandparents? Or bigger structures like archetypes, equivalent of. Is that possible? Have you tried that? Or is that desirable for anyone? Or is that way too much? It's like preparing too much for people.
So Jim talked about that, and he said he thought it was too much, right? He thought it was just at a too high level. From my perspective, archetypes, he said what I agree with what he said about archetypes, and I teach in my class. Archetypes are not model structure. They are like a design pattern that we have in programming. They show you how to develop something, but they don't tell you it's not actually developed. It's going to be different. Every archetype represents many, many different models. So you wouldn't do it at that level. And I don't know how much work has been done on tying these together into useful, reusable structures. And be some work done on that. There has been some. There's been a little bit of work. There was a review of all the work that's been done on this recently by, I can't remember. I can't believe I can't remember. It was in the SDR, not, I say not too long ago. It could have been 7 years ago.
Right. So yeah, okay. So it's a possibility, but it might be maybe a bit patronizing, or I guess maybe showing too much of a way of, I don't know, preparing too much. I'm thinking of components that we know that, okay, for example, there was an example, I think somebody was saying about doors and windows in the beginning. I think it was Jim, or no, it was Bob. I mean, imagine you have, and of course we do have like rooms. Okay, then, okay, instead of doors and windows and walls, then you get rooms prefabricated. But that would be too much of a module, I suppose. And then you don't have much creativity, or maybe just an idea.
The problem is, I mean, there are larger structures that people say are usable, but no one's come to a place where there's a catalog of those that I know of. For example, in certain circumstances, you can use the market growth model, but it doesn't work in many circumstances. So, and that's just a small number of these things thrown together. It's not that big a model. I think that's the biggest issue. You usually end up custom creating small parts of it. Even when we were working with IBM 7 years ago, and 6 and 7 years ago, and we were looking at trying to build these things up and come up with pieces that made sense, that you would only have to automate some of this development. And the problem we kept running into is, and we were going to still try, except then IBM decided to go in a different direction. But the problem we kept running into is there's always something at the higher level that's going to be completely different than what you originally had.
Right.
We couldn't find any case where that it stayed the same.
Yeah, okay.
The structure could be the same, but then you'd have to customize it.
Sure.
So that's the approach we were taking. We were trying to find structures, a little larger structures that you could then customize.
Yeah.
Also build macros. Sometimes there's common structures that are bigger than these molecules that you can reuse as macros, and then they're built-in functions. So smooth, but he considers smooth a built-in, so I don't know. I mean a molecule. So yeah. It's a tough question.
Yeah.
At that
okay.
level.
Thanks for sharing, Karim.
Okay. Any other questions for Karim? I feel like this is a Karim hosted event.
Well, the video just ended, right? There was another question in the email, which was, who uses the standard method? And I know we're almost out of time, but I'd be curious to hear other people's opinions on that. I can tell you mine, but I don't want to do all the talking.
In the limited time, let us know what yours is.
Well, Rafik, you've been in my class. What do I teach? Do I teach the standard method or something crazy? As far as I can tell, I'm familiar with what many people do. And I don't think there's a huge difference between what most people do. We can call it the standard method, or we can call it the agile method, or we can call it whatever we want to call it. The point is, the standard method is iterative. And you can move through that and come back again as many. That's the agile method, which is what, by the way, most of us do anyway. Just Tim Warren gave it a name. And the only other big difference that I see between what people do is whether or not to draw a dynamic hypothesis before you start. There's a lot of controversy about that. So Jay Forster was against it. Barry Richmond was against it. Everyone who followed Barry Richmond was against it, except me. I think it's useful. I think it's useful to know what it is you think is driving this, and then compare your model against it when you're done and see if you really actually built what you thought you were trying to build, or you were wrong about your assumptions. I think that's useful. But the problem and the reason why most people shy away from it, the ones who do and say you shouldn't do it, is people tend to build these giant CLDs. They don't build this tiny couple of things, couple loops, dynamic hypotheses. They build these giant CLDs that really are not dynamic hypotheses. And that, if you're going to do that, you may as well build the model, because the problem with CLDs is you don't have the stock and flow language, and so there's no discipline. And that's the big complaint. And that's why people don't want you to use it. One of the things, by the way, that caused that, I will say, in the 70s anyway, Jay Forster's Principles of Systems was the leading textbook. And the companion guide was Michael Goodman's Study Notes in System Dynamics. And that was written specifically to go with Principles of Systems as a pair to be used in the classroom. And by the way, Principles of Systems is pretty opaque compared to some other writings. Just to warn you, if you think you want to run out and read it. But Study Notes isn't very opaque, but it does have a very strong reliance on CLDs and large, complex CLDs that are as detailed as a model. And that's where a lot of people got that habit, I think. To me, why are you wasting your time? Just build a model if you're going to get that detailed. It's not telling you anything. And you can run a lot of risks because you may put things in there that make no sense at all because it's neither stock nor flow.
Thank you. This is very helpful.
So we're 1 minute after the hour. I apologize for people who had a time confusion, and please feel free to leave if you have another meeting, or if people are willing to stay, I have some time.
By the way, that's the Amazon behind me.
Oh, really?
Yes. Actually, it's at the part where they call it the Solomons, but we call it the Amazon still. It's west of Manaus, near Manica, Peru. And I did take that picture.
Oh, so this means
only the picture of Oregon. It's the only picture I've used that I didn't take.
That's a good use of pictures that we take, is to be at least use them as Zoom backgrounds.
Yes, and I see you're still in Cape Cod in that rental.
Yeah, that would be too expensive by now.
Okay, I'll stop the recording then.